Hey guys, so let's go ahead and look at just basic inference rules for for just propositional logic. Just go ahead and dive right in. So now that this is going to definitely build off a comfortability with just the line with just propositional logic's language, which is just composed of capital letters, P, Q, R, as many as we need, right? There's no limit to the amount of propositions we can consider. Just for whatever reason, we often look at these three, and then the logical operators, right, that we can use to connect those things. And so, understanding not just how to read these sentences, like a sentence like P and Q, like that this says P is true and Q is true, as opposed to like P is true or Q is true. So not only do we not want to know how to read these, but we also want to understand what are they saying is true. So what are the truth conditions? And that comes down to the truth tables, right? So a proposition like that is true just in case when we look at the P and Q, we have true propositions here, or so first we lay out every different way the world could go. So right, so that's false. That's false. That's true. Sloppy early. Okay, so we want to look at every different way the world could go. So there's the world where they're both true. There's the world where P is true but Q is false, vice versa, and finally where neither is true. And we find the only time that the complicated sentence, P and Q, any sort of conjunction is true, is when it's two conjuncts are true, right? So the sentence as a whole is called the conjunction, and then either side are the conjuncts. So, and if we don't have either one of them, then it's automatically false. So basically, the idea in well, so one thing we could see from this is that suppose you already start off knowing that P and Q is true, right? Okay, so one thing we're going to talk about, and I'll make this a little bit more formal or defined in a minute. We're going to start from a series of sentences. We're going to start from a series of sentences like P and Q, if Q, then R. And the idea is we're going to want to get to, at the end of the day, some conclusion, like, I don't know, like that R is true. So, again, I'll talk about this more. But so we can see how truth tables can help, though, at least to start. So if you start off with a proposition like P is true and Q is true, right? This guy right here. So premise one here. And we start off by assuming that this is just true, right? Like that's what it means when we write premises up here. And we start off believing that this is true, then that's us saying, hey, we're in this world. I'm gonna assume that P is true and Q is true. And so I'm assuming that I'm in this world. Because there's no other world that it's true. So with other truth tables, we wouldn't be able to do the same inference. Like if this was OR, right? If that was an OR, then we'd have true, 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 and false. In place of what we have there. And so we wouldn't be able to just immediately know, oh, I'm in the first world. I wouldn't be sure, am I in the first world? Oh, I might be in the second world or the third world, because if all I know is that I'm starting off with this being true, I don't know, like there's a lot of different ways it could be true. But the idea is because we have an and here, so let me go ahead and erase the or. I'm going to put it in a different color probably. So because we have an and right here, we know, and again, because we're assuming that this conjunction is true, we know we're in this world, which means we know something about either side, right? So the idea is if you ever start off with an and as a premise, one of the first rule, so the first rule we'll go ahead and see right now is called simplification, which says if you ever have this as a premise, then you can immediately deduce just any one statement, right? If you know that that is true, then you immediately can infer that just one of the statements alone is true, right? Now, you can't do that with everything. I mean, so with P or Q, like that truth table was different. So let me change the color there. So simp only works with and let's see why. So with P or Q, if this was an or, well, then we'd have the values of true still. But this would also be true, remember? So that's why it's very important to be comfortable with those truth tables, right? Or is going to be true so long as one of the sides is true. So if we're thinking about this as an or now, we have trues for the first three and only a false for the last one. So the idea is if I just start off believing that an or statement is true, I think that's a plus, just true. I can't just infer that, oh, P must be true, because I don't know which world I'm in. I don't know if I'm in the top world where they're both true, in the second world where just the left side is true, or in the third one where just the right side is true, right? Just by knowing that I'm in this world doesn't tell me, or just by knowing that this proposition is true doesn't tell me anything else. So one common mistake you see, see people making is that they just arbitrarily will start like tearing apart sentences. And it's just very crucial that you understand the way that we're going to manipulate these sentences is tied to the truth tables. It's completely tied to what we can infer from the truth tables. So I'm going to make this more formal in just a second, or give it a more rigorous background. But I just want to make at least clear all of what we're about to do is motivated by the truth tables, is motivated by, okay, the relationships between complicated sentences, it all depends on, the structure of these logical operators. And so, and that's completely made clear by just truth tables. So everything we're going to do here is going to be kind of in the background justified by truth tables. So let's go ahead and begin. So what's the difference if all we're doing is basically just going to be truth tables, or just like if it's all just boils down to truth tables, why are we doing what we're doing? And I mean, one of the reasons is because if you're doing a truth table, like well, let's first back up for a second. So what we're interested in logic is, of course, valid arguments, right? That's the name of the game. That's how we start the semester. We're talking about trying to find valid arguments. This is 100% the most important notion in logic. This is what it's all about. This is what we're trying to figure out. And it's a very subtle notion that a lot of people still don't get by the end of the course. Basically, and if you don't get it, then basically all you've done is just learn some board game rules, which might be fun, I don't know, depending on who you are, but really understanding what validity is, that's what's going to help you reason better and write better and think better. Make it right. So anyway, the point of a valid argument, so what's an argument first? Right, so a valid argument is just a specific type of argument. So an argument is a list of sentences. 1, 2, 3, ... As many as you want. Maybe it's just one. Maybe it's 0. We'll talk about that another time. And then a conclusion. So this symbol right here, these 3 dots, just 1, 2, 3, that just means therefore. All right. That's probably not the easiest thing to read. But the idea is, an argument is a list of sentences where the last one is the conclusion and the rest are premises. Okay, so the idea is we have a conclusion down here, and we have premise one, premise two, and you get the idea. And so the idea is a valid argument. I'll go ahead and write this up here. So the idea behind a valid argument is that there's no possible way for the conclusion to be false while the premises are true. So let's think about that for a second, just to make sure we're all on the same page, because this is so vital to doing a proof. You can't do proofs on an argument that isn't valid, right? This isn't proving something's valid is going to be proving an objective feature about some list of sentences, an objective feature that depends on the structure or the order in which the sentences have been connected. So, so the idea here is that one way to show that an argument is valid is something like this. So like if I have the argument premise one is, so I don't need it to be as big anymore. If I have the argument that premise one is if P then Q, right? So this is that conditional. Or you know what, just because the conditional, that can be harder to get used to. So let's go ahead and keep it even simpler with just the disjunction. So remember the truth table for the disjunction is just going to be, well, we'll look at that in just a second, but just consider this argument. So the idea here is we have two premises and there's always just going to be one conclusion. But the idea is we start off assuming that these premises are true. And we question, is there any possible way the conclusion could be false? Right? So that's at least one way to attach this. You could also just start off, let's assume that the conclusion is false and ask, is there any possible way that the premises are true at that time? Now, it's really important that you realize it's all about possibility. So this has nothing to do, or this isn't about what's true in the actual world. That's not what makes an argument valid. So a great example of a valid argument is, so let me go ahead and erase a little bit. A great example of a valid argument is the following. So if we had something like, if we had something like, I'll just write this in English. All cats are orange. I'm a cat. Therefore, I'm orange. Right? So let's think for a second, is this argument valid? And so we have these two premises, and so we're going to ask the question, is there any possible way for the conclusion to ever be false if the premises were true? So again, I do not care about the truth here. The truth just does not matter for validity. When I say the truth doesn't matter, I'm talking about the truth in the real world, whether or not all cats are in fact orange, or whether or not I'm a cat. All that matters is, if this was true, and if this was true, is there any way that this would be false? Now, right now with the propositional logic we're doing here, we're not going to be able to prove this argument. We're going to have to wait till we do the predicate logic. So let's go ahead and, so I think this is one of my go-to, or if not my go-to argument for something where it should be clear. So before I wipe this away, it should be clear. Validity, this is a valid argument, because if you did think that all cats were orange, or you go to that fantasy world where all cats are orange, and also in that fantasy world I'm a cat, well, there's no possible way that I'm not orange. If I wasn't, then I'm either not a cat, or you just found a cat that's not orange, right? But it's fine that we're going into, a fantasy world or whatever. We're just trying to figure out what possibly what's possible given the premises. Do the premises force some conclusion to be true? Now, an important extra notion here is called soundness. And that's the other piece of the pie. You might think, like, why do I care about validity if such a weird argument like that is valid? Like, that's what a good argument is? Like, I can be talking about all cats being orange, and that's supposed to be a good argument? How is that supposed to teach me how to reason better? But the point is to just be able to separate the notion of validity, what we just looked at, from the notion of soundness. And soundness is just validity plus truth. Okay, so the idea here is that there's two questions you can always ask when somebody gives you an argument. When somebody gives you reasons to believe something, and then the thing they're trying to justify, there's always two questions you can ask, and those are the only ones you'll ever need. First, you can ask, even if I start with your starting points, am I going to have to end with your conclusion? That's what validity is. It says, okay, maybe your data is even bad. I'm just going to pretend that it's good for right now. Like, so maybe your premises are that you had certain observations of scientific data or something like that. And from there, you're trying to conclude some scientific theory or belief or something. Maybe you have observations about global warming or something like that, and you have observations about temperature change, and you're trying to make the conclusion that global warming exists, or that humans had an effect. So first thing to do is be able to distinguish what are my supporting reasons. So those are our premises. Those are the things that we're going to start from. And so we're going to distinguish our supporting reasons from what we're actually trying to conclude from there. So, for instance, is your conclusion that is your conclusion something about God existing, and your premises are that the Bible only tells truths? Or is it that your premises are that the Bible only tells truths and your conclusion is that God exists, or something like that? Or, there's very sophisticated ways there's a very sophisticated literature on arguments about the existence of God to and from. That's very entertaining. Or not just entertaining, but legitimately interesting. And so that's, especially working with Dr. Menzel, who focuses on those, that's where those examples are coming from when I bring them up. But the idea is we can think about any example or any topic. We first have to just identify what are the starting points, what are the premises that you're basing a belief off of, and what are you trying to entail? And what are you trying to convince us of? And so from there, we can ask, okay, even if I assume that your premises are actually true, can you get me to the conclusion? And then secondly, I'll ask the soundness question. After I check the validity box, then I'm going to check the truth box. Are these two premises actually true? And doing that and verifying whether or not those are actually true, one way is maybe you just devise another argument. You devise another argument where those premises are, so one argument for that premise and then another argument for the other premise. We won't be getting into anything like this, but this is what philosophers do. Or what scientists do is they've tried to empirically verify these premises. But still, all that they're able to do eventually, or all that they're able to do at the end of the day, all that they can do, is after they've gotten those observations, they need to logically entail that conclusions follow. So any scientific paper you ever read, or any reasonable argument, is somehow appealing to these rules of logic that we're about to learn, which ultimately are going to sit on those truth tables. So let's get back to maybe these particular rules a bit more. This has all just been very broad strokes, and you're still warranted to not know really too much of what's going on. But at this point, hopefully it's clear. Validity, the reason why we're doing this, validity and soundness, is we're going to set aside the question of, are my premises actually true? And we're just going to assume they are. Because what logic is about isn't doing like any empirical tests on if my premises are true. All I'll be able to do is really just do another argument and just work it back up. And hopefully I'll get to just some very obvious premises that we all agree on higher up. So all we can do here is we just assume that we both agree with them. Maybe I'll challenge soundness later, or maybe they just are very obvious premises. Maybe this is saying like, well, either you're a mammal, or so I don't want to just do a dichotomy because I don't want to confuse it. But like, if this is a fork in the road or something like that, like a fork in the road that we all know about, and P means you drive left. P means we go left. And then Q means we go right. Right. So if we have this this fork in the road right here, then the idea is we're just going to assume that we already accept that that's true, that we either have to go left or we have to go right. Right. That's what premise number one is saying. And the point of logic is we're not going to try to verify and go out and look in the world like, do I actually know that? The point is we're just trying to investigate, given certain beliefs, what other beliefs have to follow. So right, and so no matter what, no matter how much observing in the world we're going to do, we're going to need to make some inferences and actually entail some beliefs. But anyway, let's actually get to it. So here what we have is we're starting off believing, so we're going to assume that premise one and premise two are true. So we can think about that in terms of a truth table where we have P or Q, and we have not Q, and we have P down here. And then let me go ahead and separate those a little bit more. And then we can do this, P, Q. And so, right, so P can be true while Q is true, P can be true while Q is false, P can be false while Q is true, P can be false while Q is false. Okay, and we can just kind of fill out the truth table to really understand what's going on with this argument. So in this case, we would have, right, so the or statement is true when either side are, are true. So we have true, 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 false. The negation, we're just going to flip the values for Q. So false, true, false, true. And then P, it's just going to be whatever P was. True, true, false, false. So again, the idea is in the first world where P is true and Q is true, the statement either P or Q is true, and the statement not Q is false, but the statement P is true. But, right, so that's just reminding us on how we translate things. Well, let's just real quick bounce back to the definition of validity. The point of validity is that there's no possible way for the conclusion to be false while the premises, I don't know where that P went, are true. Right? So what we need to check in order to know if this argument is valid is there any row, is there any world where the premises are both true, but the conclusion is not? Right? So, I mean, we can first just think about this argument intuitively. It's saying either P is true or Q is true. You're right. So one of them is true. Q is not true. So one isn't telling us that they're both true. So like I'm still open to believing that one of them could fail. And then it's saying Q is in fact not true. So I'm fine with that. Like that's not contradicting it, but it does tell me. So below this line is us. That's where we get the conclusion. Okay, because I know we started off believing one of them had to be true, and then I found out that this one isn't, well then the other one really has to be. I have no choice. One of them had to be. I ruled this one out. It's the process of elimination. And we can see that really quickly with the truth table, right? So we'll just check every row. Do we have true premises? No. So it doesn't even matter if the conclusion didn't follow. The only way for this argument to fail is if both of the premises are true and the conclusion turns out false. So world one doesn't invalidate us. World two, we're still okay because everything is true. World three, we have a true premise and a false conclusion, but it's okay that the conclusion's false because one of the premises is false. Like the point of the argument, it's saying, I guarantee you that the conclusion will follow, but I only guarantee you that if you start off with all of my premises. So if even one of the premises fails here, then that's not showing that the argument's a bad argument by any means. It's still a completely fine argument. So again, let me just make this clear. The only way that this could have ever failed is if it came up looking like T, T, F. That's what would have been an invalid argument. And then you would have looked over here and you would have seen like, oh, shoot. So when P is like true or something and Q is something or other, right, there in fact is no world. But like certain arguments will be invalid. But the point is, there's no possible way here. There's no world where we can accept that both premises are actually true while accepting that the conclusion is false, right? So all that stuff at the end, like there's no way that can happen. So let me say it in just another way, because understanding validity again is so vital to this entire class, and we don't get to talk about it often enough, to be honest. So another way to think about this is just go to any world where both of the premises actually hold and ask yourself, does the conclusion hold? And if every time you check that both the premises hold, the conclusion also holds, that's what it means for the argument to be valid. And so this has just been, so right here we've just verified the argument's valid using a truth table. But the idea is that's actually going to be a real pain to continue. Because a truth table works by checking absolutely every possible combination of the truth values of the atomic sentences. Well, let's just think for a second what that really means. So if I have an argument that's like A and B implies C, not D or F, therefore A and B. I'm throwing things around right here. I'm not really thinking through. But the point is, we don't really need to think through this argument too much to see this would be a miserable thing to do a truth table on. Like, the symbols are actually really straightforward. There's not too many symbols. But the thing that makes it so miserable is I have A, B, C, D, F, 5 different atomic sentences that I need to worry about varying. Right, so that means I need to worry about F being true or false, it being true or false while D is true or false. All of that could happen while C is true or while C is false. Right, so all I'm going to do is just copy all of this down, right? It's just going to be the same thing, just copied down below, because all of that can happen while C is being false. And then we're just going to do the same thing. I got to copy all of those rows down again for when B is true. All of that could happen while B is true. And then all of it could happen while B is false. And then I got to do it again for A. So the point is, every new symbol, every new sentence I put in, I have to double the size of my truth table. And that just gets ridiculous. We don't want to be kept like that. We don't want to be forced to do that much work. So the idea is, instead of that, what we're going to do is we're going to utilize various rules. So that argument P or Q, oops, we have one more premise, not Q. This, because it's so, we just showed how this is a very, we just showed how this argument is valid, right here. So the idea is, we're going to take a handful of these really obvious valid arguments like this one, and we're just going to say that's a rule. We're just going to call it a rule. And what that means is, whenever you have a list of sentences that looks like this, you can just give yourself that one on a new line. And so what a proof is going to turn out to be is, we're going to start off with some things up here called premises. Right, premise 1, 2. And then what we're going to do is we're going to use really innocent arguments like this one. So that's what all of these rules are going to turn out to be. They just all boil down to really innocent arguments that we can verify via a truth table. So this one we call disjunctive syllogism, because we have a disjunction, and a syllogism is another name for an argument. So either P or Q, but not Q, well then it's got to be P. So that's such a plain as day, obvious, valid argument, and even if it wasn't, we just proved it was via the truth table. So now the idea is, anytime we have a premise that says stuff or junk, and then we have another premise that rules out one of those sides, we know the other side has to be true. Right? And so this is just going to be a general form that we're going to watch out for. We're going to watch out for disjunctions, and then watch out for other premises that are just negating one of the sides. And if we can find that, we get one of those, we get the other side for free. And so the name of the game is going to we're going to use those innocent rules to keep giving ourselves newer lines until eventually we get to that conclusion we wanted to get to. So in the case of this argument, the conclusion was right away, and that's why we turned this into a rule. But like some arguments, it's going to be harder to do. So let me just clear this. So some arguments it's going to be harder to do. So for instance, let's do P and Q. Or R, it's an and, that should be a little bit higher. Or R, so that's premise 1. And now we have premise 2, and let's call that just not R. And let's just suppose at the end of the day, we want to get to, so that's all these 3 dots mean, want to get to, let's say I want to get to P. So the way you can think about this is, me and my guy that I'm arguing with, we both believe 2 premises. We're going to both assume that these 2 things are right. And now we're going to figure out, I'm going to try and convince him that based on these two premises, there's no way he should deny P. That may not be obvious. Like certainly before you learned all the logical symbols and stuff, that wouldn't be obvious. And maybe to some of you, it's still not obvious. But let's think about what the sentences say. So one is saying either, right, main operator, we read that first, either P and Q are true or R is true. But R is not true. So therefore, we want to believe that P is true. Maybe other things are true too, but we at least want to get them to believe P is true. Okay, so the idea there is we're just going to use the DS rule that says if you ever have, so I'm going to use colors here, if you ever have stuff, so these are just Greek symbols, but I'm not even going to use the Greek word, I'm just going to say stuff. If you ever have stuff or you have junk, but then you know it's not the case that junk, so I'm worried that the Greek symbols might be even more confusing than just stuff and junk. So let's for the time being at least. So DS says if you ever have stuff or junk, I don't care how complicated those sentences are, and then you can negate one of those whole sentences, I'll give you the other one. And we're going to use that right here. Oh, I said I wanted to use colors, so let me do that. So there's that. So right, so hopefully using the colors makes it clear the structure here. All we care about is that there's a disjunction that's the main operator. So all these rules are going to be worrying about the main operator, at least for these implication rules. I'll talk about that more in a moment. What I mean by implication rules. But the idea is if you ever have a sentence that has an or as the main operator, and then you find the negation of one of the sides of that or, you can get the other side. So here we have the or as the main operator. Then we've negated one of the sides of that or on another line. And so what we can get from that is just P and Q. So here, right, so let me take away that conclusion. So here, right, R corresponds to junk over here, is the green. And then the idea is P and Q corresponds to our blue stuff. So we negated one side of the disjunction so we have a disjunction. On another line, one of the sides of the disjunction is negated. So all that means is, just like over here, we get to take that other side and throw it at the bottom. So I'm just going to take that other side and throw it at the bottom. And so now that's a new line. So the idea is anything I've proven, so these we assume from the get-go. These are the premises. But then any new things I've proven, well, he knows this now. So now I can use this to further make my case. And this is where we can use the simp rule that we were talking about earlier. And so the simp rule says if you have stuff, spoiler. So the simp rule is going to say if you have stuff and junk, well, you actually don't even need anything else. If you have stuff and junk, just that line, well, you can just go right to just saying stuff. So the next thing I wanted to do was I wanted to just get them to believe P at the end of the day. So a proof is only ever over when the last line is exactly what you're trying to get them to believe. This might feel trivial, like, wait, right here it says you already believe P and Q. But the point is, we don't want to force him to do any thinking like that. We need to show very explicitly, no, look at that line. That line is where you believe P. And if you're thinking it's so trivial, well, then it should be a really easy move. And I mean, in fact, it is. You're just simplifying that line to get to what you really want to talk about. And I mean, that's something that can happen and conversations. Really what you need to do is narrow down what the actual conclusion is and stop talking about the extra noise. So let me go ahead and clean this up just a tad and show how we would. Okay, so I'm going to. So the idea here is we had this argument P and Q or R and not R. So we believed two things here. And then from there, we wanted to be convinced of P. And so the first thing we did was, and this is what we're going to have to do in every proof, we're going to have to give a new thing that we believe and then the justification. So here we entailed P and Q, and we got that. First we give the rule, and then we give the line numbers that they came from. So the rule was DS, right? That was the inference we made. That's the structure we used first. It had nothing to do with simp originally. It was just a DS. And the lines we were using are 1 and 2, right? As these proofs go on, they're going to turn really long, and you're going to need to specify, no, those are the lines that I'm doing this rule on, and that's how I'm getting this new guy. Okay, and then the next thing we did was we just did a simp. And what line did we do it to? Well, now it had nothing to do with 1 and 2. All we did at this point was we noticed 3. 3 is just on its own now. It's just as good of a line. You don't have to care about where it came from. Now all we know is 3 has that conjunction form, and so I'm able to do a simp on 3 and give myself P, and boom, I have the conclusion. So what these proofs are going to turn out to be is just figuring out when and where to use these rules and on what lines you can use these rules in order to find your conclusion. It's going to be just puzzle solving. It's going to be about trying to figure out how you can unpack the sentences, and you can only unpack the sentences using the rules themselves. So understanding simp, understanding DS, those are two of the most fundamental rules that we need to get clear on just very quickly, because when you see it in a proof, it needs to be more or less just automatic that you can do that, as opposed to just, I mean, it needs to be like that the carpenter who just knows what the hammer's for, as opposed to just a carpenter who sees he has a lot of work to do and then has to look at the book full of instruments and tools that he has, right? You need to just know what things are good for without having to survey a list of things. Right, and so simp and DS are going to be two of your most useful tools. It lets you take this or, and then if you can rule out one side, you get the other side. That's going to be very useful. It's like a process of elimination. And then simp is, okay, you're talking about a lot of things. Let's just narrow it down to talk about one thing. Right, and we'll talk about, and as we go through examples, it'll be more and more clear what these things are good for. Okay. Okay, so that's simp and DS. So those are two of our most simple rules. Right. And so as we go through, it's going to be good just in your head to keep a catalog. So I think there's going to be like 18 rules in this rule set. Just for the record, there's multiple rule sets that we could learn. Some of them, there's pros and cons to, there's pros and cons to different systems. Right. So just as a warning for other sources of logic that talk about different rules, I mean, any textbook is going to be using a rule system that's fully complete and can do everything we want to do, but it might just look a lot different. But right, so we're going to want to keep a catalog of the rules we have, and one way to think about this is by the number of lines that they use. Number of lines used. Well, so all of them are going to be judged by this. So some of these things are going to use only one line. some of them 2 lines, right? There's really no, some of them 3 lines, etc. Or actually, that's it right there. It's so all these rules, no rule is going to use any more than 3 lines. In fact, only one rule uses even 3 lines. So really, all these rules we have are going to be based on really simple arguments that just go from either 1 line or 2 lines to another conclusion. So it's just going to take really simple steps from, okay, you believe those 2 things? Well, in a sense, you can kind of just mix those together and get another thing. And so that's how these are going to go. So simp just cites 1 line. It just says, if you give me 1 conjunction, I'll give you another line, and it's just going to be one of those conjuncts. DS always and only cites 2 lines. You have to give it a disjunction and the negation of one of those disjuncts, right? That's the only way it works. It only works if you have stuff or junk on 1 line and then not junk on another line, or not stuff, right? In which case you would get junk. But anyway, okay. So it'll be good to try to keep this catalog as we go of rules. Again, they almost all use either 1 or 2. It's just the one rule that actually uses 3 lines. But hopefully at this point, it's at least simple what we're trying to do. We're trying to go from a set of sentences to some sentence to another sentence that's previously determined. It doesn't have to be P. It could be complicated in itself. Maybe it's P and Q or something like that implies R. You know, maybe that's what we want to prove to him, that if P and Q are true, then R is true. And the idea is we have to be able to use these lines to get there. And what does it mean to use these lines to get there? Well, we can use the rules we have. The rules tell us when the lines are given or in a certain form, then they entail other sentences. So when you believe something of the form P or Q is true, and you also believe that Q is just not true, so you believe you're either going to get a puppy or a cat for Christmas, but you know that you're actually not going to get a cat for Christmas because your brother's allergic, well, then you get to entail that you are going to get a cat for Christmas, or a puppy, whichever one I said your brother's not allergic to. Right. So the idea is we're going to use these very innocent little arguments, these innocent little rules to do things. So every time you do a rule, you should be thinking, you should be able to ask yourself, why does this make sense? Why does this new line I'm getting, why is this justified from the other 2 lines? And if you can't tell yourself that every time, then that must mean you don't understand the rules. I mean, that's just the truth about it. So as you're going through these, and like one of the biggest problems I'll see is people just citing a rule in the wrong number of lines or something, or just not knowing exactly. They think they know how to tear things apart. Well, if you're not using the rules, then you simply don't know what you're doing. Okay. So, all right. So let's go ahead and look at a number of rules. 1 second. So here we have just, I guess you can't see my rules list. I don't believe I can right now. Okay. So what we're going to do here is just go ahead and look at a variety of other rules. So you've already seen one example of a proof there. Probably one of the most important rules, if not the most important rule in this rule set, is called Modus Ponens. And this is going to be the most important one for you to get, or one of the most important. Simp and DS are also up there, but Modus Ponens says if you have a conditional, and really I mentioned in another video where I've mentioned before, so there's no need to do all, but that we don't actually need the conditional. It's actually just an extra symbol because it has a lot of things just become very intuitive, or it makes proofs intuitive. And here's an example of where. So the idea is, if you have premise 1 and premise 2, so premise 1 says that P leads to Q, that if P is true, then Q is true. And then premise 2 says, in fact, P is true. I mean, we can bounce back to the truth table if we need to, right? Only ever true in the second row where you have a T going to an F. Oops, that's a false, that's a T. Right, so if we're saying that this one is true, that means, so right, we're always going to assume that our premises are true. So that means we're ruling out that world. And now you're also telling me that P is true. So that means we have to be, we're ruling out that world too, right? So P, Q. So we're ruling out that world because P is false. We're ruling out that world. So that means we must be in this world. And what else is going on? Oh, look at that. Q is also true. Right? And I mean, that should just be, that's exactly the reason why we even incorporate this symbol, is basically for this rule, is for us to do this super obvious, like this is one of the most intuitive, if not the most intuitive inferences we want to make. That if P entails Q, like the whole point of this sentence, what that sentence means is just that if P is true, then you're going to get Q. So this should be a very intuitive rule, and if it's not, then this is one that definitely deserves your attention, and for you to spend extra time on just practicing it. So I wanted to actually, let me go ahead and write that in the color, because it's going to be very important for, it's going to be very, a lot of people get lost on when you can actually do modus ponens because of how complicated the sentences get. And the important thing is just understanding it's just about the structure. It's just about, you have this main operator, and it's saying, if the left side is true, then I'll give you the right side. That's all premise 1 says. And then premise 2 says, hey, look at that. I've got the left side for you right here. So the point of this rule is it's saying, okay, there you go. You get the right side. Premise 1 told you the left side gives you the right side. Premise 2 says you do, in fact, have the left side. So, well, if every time it's Wednesday you have logic class, and it is Wednesday, well, then you have to have logic class. There are a few things more intuitive, I think, in this class. So yes, you should definitely spend time. If that wasn't obvious, you should definitely spend time rewatching this video, or emailing for questions, or practicing these things, because understanding when modus ponens works here, like that should not be where you're getting stuck. That should be what you're praying to see, is a modus ponens. Modus ponens is really the logician's bread and butter, given this rule set. Okay. I'm spending more time on modus ponens as well as those first couple rules. First couple rules just to give you a taste of what are we doing in proofs. Modus ponens now because it's so important, but I would like to try to pick up the pace just a tad. Okay, so that's modus ponens. Now, while let's go ahead and look at some others that I think, before we get into almost what I would call fancier rules, I'm going to just do a couple just very important rules that we need to look at. And these might even seem just super trivial, but that's fine. We still need them. For instance, if we ever have premise 1 saying something like P, and remember, whenever I say like P, this could be as complicated as we want. It could be P and Q or R, right? And we're just going to treat this as a block. But we'll talk about that. I'll do an example of that in just a moment. But the idea behind this rule that we'll do now is, if you ever have a sentence P and you also assume Q, so these are our premises, these are our starting points. Well then, surprise, surprise, you should believe P and Q. And this is just conj, and this is 1, 2, right? So conjugation or conj just says if you have two lines, you can just put them together with an and in between, right? And so, I mean, you might be thinking like, why do I ever want that? But like, the point of proofs is that you're a lot of times going to have to problem solve. So like if we had so keep modus ponens in mind, you're definitely going to want to have that, but I need to erase it for this space. If we have an argument that says something like P, Q, if P and Q, then R, and we want to entail, like we want to convince the guy to believe R based on these three propositions, well, modus ponens, you can't do modus ponens right now, right? Modus ponens requires you to have a conditional, right? So modus ponens, we might as well go ahead and throw down in here, this one of those two-liners. And what's one of those lines? Well, most importantly, we need to have a conditional. Okay, cool, we have that conditional, cool. But not just the conditional, we also need to have the left side of that conditional, right? So let me go ahead and write the rule up here again. If P then Q, you have P, give yourself Q. So actually, let me not do it with P's and Q's because I don't want to confuse it over here. It's just if stuff, then junk. And suppose you actually have stuff. Then on a new line, you know junk has to be true. You can convince him 100% junk has to be true, given that stuff implies junk and you actually know stuff is true. Remember, like the conditional, it's not telling you that stuff is true or that junk is true. It's just saying, it's just a conditional. It's just saying one condition for this is that, right? If stuff happens, then junk happens. That's all that premise, that's all that the first line says. And then line 2 is saying it in fact did happen. And so the rule is telling you, okay, now we can entail junk must have happened. But with all of this, we need to, right, if this is our conditional, so if we need to have a conditional, that's our left side. And so you better be able to look up here and find exactly this as one of your premises, P and Q. But that is neither one of our premises. Again, we cannot skip steps. This is about slowly, meticulously, every rule has to be absolutely innocent. This rule doesn't say, oh, if stuff kind of looks like this other stuff, right? P kind of looks like 1 and 2, right? Modus ponens doesn't cite 3 lines. It just cites 2 lines. You need to have the conditional, and you need to have just the left side of that conditional on its own line. But here, neither line here is exactly the left side of the conditional. So we cannot do modus ponens. But obviously, we can do something here, right? This argument is obviously or intuitively valid. If you know P, if you know Q, and you know together they lead to R, then you know we'll be able to prove R. And here's how we do it. We use the conj rule. We say, well, P is true and Q is true, right? P, Q, we put those together. And so that's just 1, 2, conj. And then on the next line, now we can use this. This is now stuff. And then R is junk. So now we get R, right? And so this is 4. Our new line is 5, which is now our conclusion. And that's just going to be 4, 3 modus ponens. You cite the conditional, and you cite the left-hand side of the conditional. But we could not have done, this is so important, you cannot do modus ponens if you don't have exactly the left side of that conditional. Okay, so again, modus ponens, super important. And one of the reasons for conjugation, and a lot of these rules like simp and conjugation are just helping you carefully, like it feels like, hey, I already have what I need to have. So these rules like conjugation and simp are just letting you break it apart a little bit more. Notice they only work, notice these rules only work for the specific connectives we're looking at. Like conj and simp, both are only for when your sentences have and as the main operator. But let me go ahead and, so that's true. But let me just also make sure it's clear. Like the sentences can be as complicated as we want, but it's just about identifying the main operator. So because that's an and, now I can do simp, right? Because simp just says if you start with stuff and junk, I'll give you stuff. So just like that means that simp, all that simp needs in order to run is just show me a conjunction and I'll give you one side. That's all that simp needs. So as soon as I see that, like if this is like premise 1 or something, as soon as I see that the main operator is a conjunction, it already fits into the simp rule. It already is a match for simp. So I can just immediately after that say, oh, well, if I know premise 1, I know that P must entail true, P must entail Q, and I also know that R must be false. So that would just be 2, 3, and 2 would be 1 simp, and then 3 would be 1 simp. In fact, so that's going to be one of the most important rules of thumb. When you see one of your premises as a conjunction, it's almost always, in fact, it'll never hurt, just split those apart. Because now, before, I couldn't do any modus ponens or anything to that guy, right? Because that's not my main operator. But now that I've simped it, I can do a modus ponens, or at least if I had a P, I can at least start thinking about using it. So it's just very important to recognize these rules work by looking at the main operator of these sentences. And that's yet again another reason why it's so important to be comfortable picking out which operators are the main ones. Which operator is the main one for that sentence. So that's conjunction. Another rule that it's important for us to talk about, without it, our system actually wouldn't be complete, and that's addition. Addition is really going, we'll turn back to the truth table to see it. Basically, it says if you believe that P is true, well, so actually, no, I need a little bit more than that. So addition utilizes the truth table of OR. So the idea is, right, we still have the same combination of things that could happen. Oops, oops, oops. And then OR is only ever going to be false if both of them don't happen, right? So the idea is, remember, a valid argument is just one where if the premise is true, if that's true, then the conclusion is also true. Like there's no way for the conclusion to be false. It's fine if sometimes the premise is false and the conclusion's true. That's fine. The point is, if the premise is true, the conclusion has to be true. There's this forcing relation. There's this entailment. And so the thing that addition utilizes is the fact that in any of these rows, let me use a different color real fast. In any of these rows, OR is going to be true. And really, the only thing you had to know for OR to be true, this complicated sentence to be true, was just that one of the sides was true. Right? So the point is, just by knowing that one side is true, you know that the OR statement is true, right? So like, if P is something like Christmas is on December 25th or something like that, then it doesn't really matter what Q is. You already know you're in one of these two worlds. Like if Q is false, sure, you're in that one. If Q is true, sure, you're in that one. Either way, OR is true. So let's think about that in terms of, that might sound fine right now, but it feels so weird when we look at this in terms of a proof structure. Because if you start with a sentence, let's just start with some premise, just P. What this is telling us is, as soon as I know P is true, I automatically know P or Q is true. So I didn't even have to know what Q even was. So I get to say P or Q. And what's weird about this? Where's Q? What's going on? This sentence has nothing to do with Q, yet I'm able to entail a sentence that has it. So let's think about why this works. I mean, you're starting with something you already believe, right? All dogs are mammals. So that must mean all dogs are mammals, or I own a dragon, right? Is there any way for that to be false? Well, not if what you started with is in fact true, not if P is in fact true. That means automatically the or, it doesn't matter how false the Q is, the or is automatically true. So that's why this rule works. Hopefully that makes some intuitive sense now based on the truth table and just generally. Again, or statements only care about one side being true. So as long as you started with one of those being true, it doesn't matter what that other side is. So the point here is, so earlier we looked at an argument. That had P and Q give you R, and we know P and we know Q, and from there we just conjoined them on the next line. So we did a conj, and that would be 2, 3, and then we did a modus ponens on 1, 4 to get R, right? So the idea was we were building the left side here in order to do our modus ponens. We were looking ahead to see, oh wait, I have a near miss for modus ponens. I know I can do a modus ponens if I can just put these things together in the right order. So that's how we did it for conj. But and that's because this was an and in there. But what happens if this was actually an or? How do things change? So I'm also going to change, I'm going to take away a premise even. So the idea here is if we want to do a modus ponens to get to our conclusion R, let's say that that's still our conclusion. We want to do a modus ponens, then we can't do it from here. But this is an or. So we don't actually even need the Q. So that's why I'm just going to leave it off, because really when this was an and, we were saying, okay, if you have P and you have Q, I'll give you R. So you needed to put P and Q together and then I'd give you R. But here, this is an or, which means you only need to either give me P or you need to give me Q, and then I'll give you R. So that's at least intuitively what's going on, but still, we can't do a modus ponens quite yet because, again, we need to be absolutely clear on what the rule says, right? The rule says you need to give me all stuff will lead to junk. So you need to give me stuff, and look at that. So this, I'll make it another color, right? So I'll give you your R. Let me take away that extra block. I'll give you your R if you can just give me the pink region, right? That's the same thing we were doing earlier, except for it was just an and up there and we had the Q already. So now we still need to play the same game. We need to somehow build that pink region, but now we don't have the Q to work with. We only have the P. But the point is what addition allows us to do is say, oh, all I need is P. And then I immediately know the disjunction P or Q, that's already, that's just got to be true. And then, so this comes from addition. And now ask yourself, what line justifies line 3? If you're thinking it's line 1, you're wrong. Right? So line 1 is in fact what we're planning ahead to use it with. But planning ahead is just part of the whole problem-solving process. If you're actually, remember, you should always be able to stop and just think, no. Why? Give yourself an intuitive reason. Why is this line true given what you're citing? because each of these steps are supposed to be extremely easy and intuitive. Addition is the most awkward one out of the bunch, I think. But even this one, as soon as you think about the truth table, you should be able to say, yeah, well, all that matters is I have one side that's true. So it's okay so that's how I'm getting this disjunction, because I have one side that's true. And then it should be obvious, this just comes from line 2. It comes from the line that you're actually adding to, right? And then the next thing we want to do is on line 4, we'll do our modus ponens to get R. And so that'll be 3-1 modus ponens, right? So addition, it feels like another weird rule. It's typically going to be used for exactly this sort of thing, where you're just building yourself up to use something later. Like you have something that says, oh, you can either use P or you can use Q, and you found one of them, and you just have to throw the other one on. It feels awkward, but it's actually, and it's not all too common. It really isn't, but some professors like to throw it in because it is an interesting thing that'll happen, and it's a good skill to build. Okay, so that's addition. I'm trying to get through all of the rules that I think are most vital, and then there's a number of rules that actually are really just kind of extra. Those are the ones I somewhat refer to as fancy rules, or they're just superfluous to some extent. Or at least we just don't need to, right? We can do without them just by doing other rules in different ways. Just like, right, anyway. The other thing, but importantly, I think some things we need to look at is stuff like double negation. So if you ever have the line that just says stuff, well, guess what? You know it's not the case that it's not, you know it's wrong to deny stuff. And similarly, if you know that it's not the case that stuff, you know that stuff is true. So this is what we call double negation, right? If you believe a proposition, then rejecting the rejection of that proposition is you also would endorse, right? If you believe that Santa exists, then when somebody says Santa doesn't exist, you would tell them they're a liar, right? It's not the case that Santa doesn't exist, right? Something like that. Now, notice something interestingly different about double negation, and it's that we can go forwards as well as backwards. We couldn't do that with something like simp. Simp also just used only one line, so DN is going to be one of these one-liners. But simp said, if you have P and you have Q, I'll give you P. But just because you have P, you can't just go right back to giving yourself Q, right? You would have to have P and Q, which, I mean, of course, if you had this, you would be able to do both. But it's a different rule we're using. Here we're doing a conj. Here we're doing two simps. But here, these are both just double negations. This is both just using the same rule to go backwards and forward. So simp and conj are kind of like two sides of the same coin, but they are just different rules. So neither one of them lets us go. Neither one of them is in itself reversible. It just reverses the other one, if you will. Whereas DN is actually reversing itself. And that's going to be a characteristic of what we call implication rules, or excuse me, equivalence rules. So let me go ahead and write that. So implication rules that's all these guys that we've looked at so far, right? In fact, maybe I should have just highlighted these in different colors. These are things that you start off with 2 lines, or 1 or 2 lines, or I mean, this guy over here, CD, our 1 3-liner, is also going to be an implication rule, and you get another line. Equivalence rules, on the other hand, are always just going to come from 1 line, and you're just going to replace it with another line. So the name of the game here is, well, it's equivalence. It's about, right? It's about these two lines, stuff and not stuff, these are equivalent to each other, is the idea. So we can swap them out. In fact, we don't even have to worry about these being the main operators. We can take them as just parts of the sentences and swap them out. Because the point is, they're just the same sentence. So double negation is a very important equivalence rule. It's going to be certainly necessary in situations where we need to do things like, you know what, let's go ahead and do it. So double negation is going to be very important when we have something like this, P or not Q. And then you know Q is true though. And you want to prove that P has to be true. So right, premise one is saying, well, either P is true or Q is false. But Q is actually true. So either I'll go to the store or we don't have milk. Right, maybe this isn't the best example, but we do have milk. So that must mean, so right, yeah, I mean, I don't know why I'd be going to store if we do have milk. But the idea is, right, so either P is actually going to be true or Q is going to fail to be true. So if Q ever fails to be true, then I know P has to pick up the slack. Or excuse me, either P has to be true or Q has to fail to be true. So here, Q is not failing to be true, right? This is the double negation at play. Q is not failing to be true. So this isn't a perfect DS match, because again, DS would ask you, okay, you've got your OR, great. Oops. DS would ask you, you've got your OR, all right, fine. That means you need to find whatever it is, you need to find whatever that right side is, or your left side, it doesn't matter. But whatever that is, you need to find it plus an extra negation. So the only way to do a DS with line 1 right here is if we had a line that looked like not Q. And that way, this matches the right-hand side of that OR. So only with that sort of line can we do a DS. But luckily, that's exactly what DN allows us to do. DN allows us to go from a statement like Q is true to just, then it's wrong that Q is false. And that's exactly what we want to say here, right? DS is saying, well, either P is true or Q is false, but it's not the case that Q is false. That's really what we want to point out. That's how we're actually going to do our DS. So the idea here, well, I'm throwing away a lot there. Right, so the idea here is we have that as a premise, and so I can't do a DS yet, so I'm going to use my DN rule to set myself up for it. So I'm going to put tilde tilde Q. And again, ask yourself, what actually justifies that line? And if you're not understanding what numbers to put there, then you're really not understanding the rule. Because the point of this process is that the number is just pointing out, well, it's obviously not going to be 3 because you can't justify yourself. The number is pointing out, no, that's the thing. That's why I know not Q is true, because Q itself is true. And if Q itself is ever true, then not Q is obviously true. And you don't have to take my word for it. We've agreed. That's one of our rules, that I can make those sorts of moves. We've agreed that I can make those transitions from, if we ever agree on this premise, then we also agree that on the double negation of that line. Okay. So, like many things in these lectures, I feel like I'm giving overkill, but I think that's more or less the point of me doing this. So we have Q there. So we've done our double negation on 2. And the idea was we were planning ahead, so now we can do a DS. So now on 4, we're going to take the negation of the right side. So here's the right side, and here's the negation of that right side, right here. So pull away a couple of those layers. So here's us negating that right side. And that's what we need to do, right? Because the rule said you need stuff or junk, and then you needed not junk. So right here, this whole thing is junk. You treat it as a unit. You respect whatever the main operator is and treat whatever's on either side as a unit. So that whole thing is junk. So right here, this inside pink is junk, and then the outside thing is just not junk, right? So from that, the rule says we can get stuff. And what is stuff? It's just P. So here's an example of using double negation in order to get to where we want to go in order to set ourselves up for a DS. You should be able to see that this is a near miss for DS. That should be increasingly intuitive as you do these examples. As you that should be one of the first things you get very comfortable with, is picking out that's really close to being a DS. Like intuitively, you're just eliminating one side, and so it has to be the other side. And so being comfortable with using DN to set yourself up to do those DSs is a very important skill to build. Okay, so that's why we're talking about this so much. Let me look at the other rules to see which other ones are just so important that we can't do without. Right, so the other equivalence rule that I would say is the other most important equivalence rule I've talked about in another video, and there's good reason, because this is so important, just understanding these lines, and that's De Morgan's. So right, and so I shouldn't need to spend too much time on this, but the idea is if you ever have a premise that says not A or B, well, you can just use De Morgan's. It's an equivalence rule, so it's always only on one line, and you get to swap it out for the other form. Or if you had not A and B, you get to swap that out for the other form. And again, because it's an equivalence rule, we're going to be able to go backwards and forwards. So if you had this one, you can go to that one. If you had that one, you can go to this one. I mean, you can't jump across because these are, right, importantly different. That's the whole. If you ever think that these actually equal each other, then you're screwing it all up. But the point is, if you ever have a negation on the outside of either a disjunct or a conjunct, you can push that negation in and just flip whichever you had. Or you can pull it out and also flip whichever you had. So like, this is going to be a really common usage of it. If for instance, if that's your premise, not A or B, honestly, it's a good idea just to do De Morgan's right away, because then you get not A and not B. And then what can you do? So that's dem 1. Then what can you do right from there? Well, now you have a conjunction. So now you can do simp. So you can do not A, 2, simp, and then you can do 4, not B, 2, simp. And right now, I mean, I haven't actually given an argument, so we don't know where we're actually going, right? In order for us to actually do a proof, we of course need to know exactly what the conclusion is, and it needs to be set up in such a way that it's in fact a valid argument. Right, and so right now it's not clear what we would be doing, but these are just generally good rules of thumb to get started with, because now that sentence is unpacked. Now I know, like premise 1, that's just a big complicated sentence. 3 and 4, that's me saying, nope, A is false, B is false. It's much more, they're going to be much more easy to work with than premise 1 is. And so these De Morgan's rules are going to be very important. Generally, I hope that this helps out, just giving you a taste of the rules. I don't have too much I don't want to spend too long just going over absolutely every single rule. Definitely not as in depth as I was doing that. But maybe I'll just try to do a super fast explanation of these that you can watch with, slow down or just replay over and over again. Generally speaking, those are the most important rules. There's other rules that are also important. Some that you also can't do without, like distribution. You're going to want to know. So I mean, we might as well start there. So distribution is just saying if you have and on the outside of an or statement like this, right? You know A is true, and you know either B or C is true. Well, then you know either A is going to be true with B or A is going to be true with C, right? So this statement is an and. It's saying two things are true. A is true. You know A is going to be true. Alan's going to the concert. And either Brittany or Caroline is going to the concert. So that's the same thing as saying either, now the main operator is an or, Alan and Brittany are going to the concert, or Alan and Caroline are going to the concert, right? So that's distribution. And what's nice about distribution is it doesn't care. It just flips just like that. So if the or started outside of those parentheses, now it's going to be inside of the parentheses. That's how I remember it. And then I also just think through the truth table, basically, or just think through the intuition. So if you have the sentence, either Alan's going to the concert or Brittany and Caroline are both going, then that's in fact actually going to be the same as saying, well, two things are true. Either Alan's going or Brittany's going, or Alan's going, and Alan's going or Caroline's going. Right, so we can go ahead. This might be slightly less intuitive than the first one. I'm not going to spend the time explaining it, but really, I'll leave it to you as an exercise. You should be able to verify this rule and any other rule that you're ever concerned about. You should be able to verify just by doing the truth table. So just set this up and say, okay, A or B and C, and then that's one line, and then do A or B and A or C. And then again, right, you want to watch for, just, okay, what's the main operators at the end of the day? And if these two guys are exactly the same in every single world, like sometimes they're false, sometimes they're true, but every time they're false, that's always in the exact same world as the other guys. Every time they're true, it's always in the exact same world as the other guy being true. Then, and I guarantee, I mean, yeah, it will happen. You can verify yourself that these two sentences are in fact equivalent. They're only true in exactly the same places. Okay. So that's distribution. That in fact is a good one to keep your eye out for because it's hard to do without it. So let me go ahead and just look at some others. So we looked at Modus Ponens, but Modus Ponens has an evil twin, Modus Tollens. So Modus Ponens says if P is true, so it says if you have a conditional that says P gives you Q, and you know, and you have P, then you can get Q. Modus Tollens, so the idea is you're working in that direction. You're saying, yep, I got this, give me that. Modus Tollens works in exactly the opposite way. Oops. There's a reason why we call it, or I call it, the evil twin, and that's because it says, well, sure, P is sufficient to give you Q. But remember how these translations work. P is sufficient to give you Q, but Q is necessary for there to be P. Right? Q is necessary for P. P is sufficient for Q. Right? So if you took the 400 level class, then you must have satisfied the necessary requirement of taking the 200 level class. Right? So that means if you did not take that 200 level class, well, what do we know? We can work backwards and say you must not have done the 400 level class, right? If taking the 400 level class requires that you satisfy the necessary requirements of taking the 200 level, but you didn't take the 200 level, then we can work backwards and say, all right, you must not have taken the 400 level. because if you did, then you would have taken the 200 level, and you didn't, just premise 2. So there you go. Right. So that's what Modus Ponens is doing. It's working backwards. So I just want to point out the important. Let me go ahead and clear. So Modus Ponens says if P then Q, and you give yourself, and you also have P, you can give Q. So this is Modus Ponens. This is great. This is your bread and butter. Modus Tollens says it starts with the same conditional, right? Any conditional. But it just says, instead of giving me the left side, the positive of the left side, give me the negative of the right side. And I'll give you not the positive of the left side, but the negative. So it's just, so this is Modus Tollens, you can do anything with that. You can make do without Modus Tollens. It's pretty useful, but like it's not going to be nearly as vital. But it's just important to realize what's going on here and to make sure that you're not thinking you cannot do this. You cannot do that, and you cannot do this. So these two are actually textbook fallacies. So these two are great. We love these. So let me go ahead and do this. So that all beautiful. Modus Ponens, Modus Tollens, beautiful. On the other hand, these guys, horrible. Never do that. Never, ever, ever do that. And what's the difference? It's very crucial that you see the difference. So here, you're saying, if you give me the left side, you better give me the actual left side. I'm saying, if today is Wednesday, then we have logic class, right? If we start with that conditional, and today is Wednesday, then we have logic class. But that doesn't mean, that's totally different from this guy. This guy down here is saying, okay, if today is Wednesday, then we have logic class, but today isn't Wednesday, so we must not have logic class. But that's bad. That is not a good inference, right? What if you have logic class on another day, right? The whole point here is that P is only a sufficient condition, but it's not necessary. There's other ways you can do it. So this comes down to the whole point of understanding the conditional and the direction of the conditional. So understanding how to do Modus Ponens and Modus Tollens, and really just comes down to knowing that you can't do it like this, that these reds at the bottom are bad and the greens at the top are good. So if you're going to go from left to right, if you have the P, then it better not be a negated P, because that doesn't tell you jack about Q. Similarly, if you're going from right to left, right, if you have something about Q, it better be the negation of Q, and you better be getting the negation of P, because the idea is you're saying you didn't have that necessary conclusion requirement, so you're not going to have done the first thing. Okay, so again, it's very important. It's very important to recognize which of these are actual good usages. So this one is called denying the antecedent. So these are such famous fallacies that they even have names. Deny, and you might have heard them. So the idea is denying the antecedent doesn't tell you anything about the consequent. The antecedent is just one way that you can prove the consequent. But it might be that P leads to Q, it might be that R leads to Q, and all I need to do is find one thing that leads to Q, and then I can get Q. So even if P fails, maybe R holds. Maybe it's not Monday, but it is Wednesday, and so I still do have logic class. So denying the antecedent is a fallacy, and similarly, affirming the consequent is a fallacy. We don't really spend too much time on fallacies in this class because we're more interested in identifying valid arguments and building the intuition on how to construct and how to think about valid arguments, which of course is about distinguishing them from invalid arguments, but this is, right, this isn't, this typically gets a little less formal because there's, right, right, we can talk about that in time, but it's not as hard to just come up with a counterexample for an invalid argument. Well, most of the time. But again, we're not going to spend too much time on that, or any time really more than this, because it's not our focus. Okay, so that's Modus Ponens, which is very important. Another thing there, so Modus Ponens was saying if P then Q, and so not Q will give you not P. So let's just think about that, what that means then. That means if you have if P then Q, like if that's one of your premises, then you know if you could ever find not Q, all you would have to do is just do a modus tollens and you would get not P. So this rule is just a one-line rule, and it's actually an equivalence rule, which means we can go backwards and forwards. And this is just called Contra Position. And so this rule is just flipping the order of the conditional. And it's just saying, okay, if P leads to Q, that means if you didn't have Q, you must not have had P. So very intuitive, and that's all we'll say about this time. Another rule, actually, a rule that is important enough that I should have said it earlier than this, is material implication. So let me just go ahead and say that. So material implication is another equivalence rule. And I think maybe the easiest way to see this is just from the truth table of PQ and then P arrow Q, not P or Q. So this should make it conclusive to you that we really actually don't need the conditional. Every conditional can just be rewritten as an or of this form. So, right, so if you're saying if P then Q is true, or well, let's just think about the other way. The only time the conditional is false is if either P is true or Q, or excuse me. So the only time the conditional is false is if both P is true and Q is false. And now let's think about that in terms of this sentence. Well, if P is true, so then not P is going to be false. And then if Q is false, well then the Q part is going to be false. So this or is flanked by two falses on either side. So that's the only time that's ever going to be false. But then on the other hand, here Q is true, so the or is happy. It's going to be true. Here it's got a little true on the right side. Here, still Q is true on the right side. Here, P is false, so not P is true. So in the last column, so let me clean this up just a tad. We have just look at that. These two sentences are in fact exactly the same. To say if P then Q is the same thing as saying, well, either P isn't going to happen then, or we will in fact have Q. Right? To say if it's Wednesday, then we have logic class, is to say, well, either it's not Wednesday, or we are going to have logic class. Right? So again, these two sentences are equivalent, and it's going to be very useful to, this rule is going to be really useful going forward. One of the main ways I think this is useful is when you have something like this as one of your premises, well, you can't do anything here, really. You can't do a double negation because there's only one negation. You can't do a De Morgan's because this is not an and it's not an or. But what we can do is let's just do a material implication, which is the rule we just learned. I didn't say it out loud. Material implication. So the idea is we just swapped, right? So equivalence rules we can do just to even parts of sentences. I don't need to do it. So premise one, the main operator is actually the tilde. That's the thing that's looking at everything. But for equivalence rules, I don't need to worry about what the main operator is. I just need to focus on just a small part of the sentence and just change just that small part of the sentence. So really, I'm going to just copy this whole thing down. So let me just, in fact, do it like that, just so you can. I'm just going to copy this whole thing down right here, so you can see really what the change is. So for an equivalence rule, you just take the entire line and put it down, and you just change exactly what you're allowed to change. So for material implication, we're allowed to change this conditional to an or and throw a tilde on right in there on the P. So what it becomes is not, oops. So we have inside the parentheses, because that's the thing we're changing. We're just changing the conditional inside the parentheses. So inside the parentheses, we have this. And then outside the parentheses, everything stays the same. It has no idea what happened. Oops, so I obviously didn't change that. So outside the parentheses still has no idea what happened. We just noted that this guy is exactly the same as this guy, so we just decided to swap him out. And then from there, now that we've swapped them out, now I can do what I wanted to do before. Now I can do my favorite rule, De Morgan's. Right? And then from there I can do a simp to get not P, as well as not Q. So right, so these are both simp, that would be a De Morgan's. So I'm getting a little sloppy already, which I shouldn't. So this isn't just an MI. And I haven't been. So this is just a MI from 1. This is a De Morgan's from 2. And then these are both simps from 3, 4, and 5. And then, okay, I mean, at this point, I might as well give a conclusion to make this an actual argument, right? So any argument has to actually come from, has to actually be about, we have some premises and we're trying to get ourselves to a conclusion. So as I'm giving you some of these techniques, a lot of times I'm omitting what conclusion we're getting to, just to give you an idea of, this is a lot of the time how these rules will work in combination. Right, and hopefully the small examples are helpful in seeing how this works. So in this case, if we were trying to get to P, the last thing we would do is just say double negation from 4. Because if I did a double negation on 4, well, I take P, not P, and I just throw away both negations, now I have P, and that's my conclusion. Okay, so in fact, I didn't even have to do that simp. It's superfluous, but that's not a problem, actually. You just convinced him of extra stuff, but that doesn't, all you needed to do was convince him of what you wanted. It doesn't matter that you convinced him of extra stuff, too. So material implication is going to be one of those that's actually pretty important. Okay, now let me just double check. Okay, all right, so hypothetical syllogism, right? I'm going to try to go fast again because material implication deserved more time, but this is another just more or less completely extra rule. So if P leads to Q and Q leads to R, well, guess what? P is going to lead to R, right? And that should be just absolutely easy to see, right? Because the idea here is, well, if you know P is true, then you're going to get Q for sure. Then right away, whenever you know Q is true, you're automatically going to get R for sure. So knowing P is just going to start off a chain reaction that ends in Q. So you can think of this as like a leapfrog rule or whatever, and we just get to cut out the middleman. So that's all HS is you're taking two conditionals, one of them picks up where the other one leaves off, and so we're just going to cut out that middleman and just talk about one. Okay, that's HS. Constructive dilemma, this is our one rule that's actually, going to be cite 3 lines. So it is an inference rule. And the idea is we're going to have one line that's a conditional that P gives, actually I want to use Q for, P gives to S, or P leads to S. Then another line is going to tell us that Q leads to R. And then a third line is going to tell us that, well, either P is true or Q is true. And then, so let's think about this. So if we think of this disjunction as kind of a fork in the road. So we either need to go left or we need to go right. Right, I know that's not the perfect metaphor, but we either need to go left or we need to go right. And then think of either one of these conditionals as bridges, right? Like continuing that road metaphor. So P or Q is saying, okay, you're driving down a road and you hit a fork, right? Let's see how that works. Right, so this is P or Q right here. So this would be going the Q route, this would be going the P route, right? And so just to connect this back to what we were talking about earlier, DS is saying something like, oh, and you also know not Q. So you also know, so let me put that somewhere else so I'm not confusing. So like DS would say, not only do you know that that's true, that you have this fork in the road, it's saying you know not Q. So it's just taking this road and it's blocking it off. And if you block off one of those roads, well, now you know, all right, I know not Q. So I know I've got to go either left, or I got to go either left or I got to go right. I can't go right, so that means I have to go left. So that's DS, just so we're all on the same page. Constructive dilemma, we can use the same sort of metaphor, except for now our conditionals, just think of them as bridges. Right. I don't know how. Right. I don't know how to draw. Okay, so but the idea is the conditionals are just bridges that tell you, like, okay, if you go like P leads to Q. As soon as you get on that bridge, or leads to S. As soon as you go the P route, you're going to end up in S. As soon as you get on the Q route, like it's a bridge. You can't turn around on a bridge. You're going to end up with R. As soon as you have Q, it'll give you R. So the idea here is if you know that you're driving down the road and you either need to go left or you need to go right, and going left will eventually lead you to S, and going right will eventually lead you to R, then at the end of the day, you know you either have to have S or you have to have R. Right? So here we have this disjunction that says one of two things is going to happen. Either P is going to be true or Q is going to be true. But if P happens, then we're going to get S. And if Q happens, then we're going to get R. So really, we know that because one of those two causes is going to happen, one of those two effects is going to have to take place. So that's constructive dilemma. And let's go ahead and move on. Simp we've done, comms we've done, addition we've done, double negation, material implication. Another rule, I'll just say real quick, is if you know A and B, that's a premise. Well, this is an equivalence rule. You know B and A. So if your premise is something like this, so if that's like premise 2 and this is premise 1, you first need to do one commutativity in order to flip the order around. Because again, what these rules care about so much, really, this is really the only, we rarely even use this rule because, I mean, yeah, it's typically not even set up like this. But this is the only time because you're just trying to make it so that the rules are happy. The rule just needs it so that that left side perfectly matches what else you're going to give it. So, right, so this should actually be 3 if this is a premise. If we have premise 1, premise 2, then this would be line 3, which we got from 2, and then 4 would be a modus ponens. Again, I'm being a little careless, omitting the fact that like these are just general strategies that when you see this sort of thing, this is something you can do. But like when we actually get to examples of like full-fledged proofs, we're always going to have a target of where we're aiming at. So, and that's going to give us a better sense of which rules we want to use in order to get there. Right, and so that's going to be much more clear when we're actually doing problems. But hopefully we're at least getting into these proofs well enough, right? So if these are your premises, oops, needs to C. I'm just not even going to worry about cleaning that up. And we're trying to get to C, right? This is how we would do it. We would first just do a com, and then we would do a modus ponens. So this is a very straightforward proof, but hopefully it's shown. Okay, let's go ahead and look at, so commutativity, associativity. Right, associativity looks a lot like some of the others, but it's also just very simple and trivial. So associativity, don't get that confused with distribution. All associativity is when you have the same operators, it doesn't matter how you group them, right? If I say I either have a dog, or it's the case that I have either a dog or a cat or a bird, well, that's the same thing as saying I either have a dog or a bird, or I have a cat. So if I'm just using the same, and it doesn't matter if these are all ands either. So associativity is just going to say that if the connectives are all the same, it doesn't matter how you group the parentheses. Now that only works for and or, right? So that does not work for conditional. Okay. That's associativity, De Morgan's, Contra Position, Exploitation. Right, so okay. Let's go ahead and just finish off the list real quick. Exploitation says is an equivalence rule. So if we have this, we can go back and forth between this and just saying, well, so this is saying, if you do both of those things, I'll give you R. So that's going to be the same thing as just doing them one at a time, saying, if you do P, then, so let's see. If you do Q, then I'll give you R. So it's like saying, so right, it's just kind of like slowing it down. You can check both boxes off at once, or you can check them off at one at a time. So like if the only way you could even run for president is if both you are American born and you're over 35 years old. So if you're American born and you're over 35 years old, you are able to run for president. Doesn't mean you have to. Right? That's the same thing as saying, if you're American born, then if you're 35, then you can run for president. Right? And so because this is an equivalence rule, we can go backwards and forwards. I'm not spending much time on it because this is one of the rules that we really, that's going to be just less important than others. Right. But these are all the sorts of things that I completely welcome email questions on. So that's exploitation, distribution we've looked at. So real quick, we can also say this, if you know P is true, you know P and P is true. That should be obvious, right? If I know I have a dog, I know I have a dog and a dog. And I can go backwards and forwards. That's another equivalence rule. So that's just reiteration. Right, so the last rule was exploitation. I apologize for not writing it out. I'm trying to finish this off so it's not too long of a video. Exploitation was the one that said that this guy is the same as this guy. Now reiteration is the one that says, okay, you can just repeat yourself. You can even repeat yourself with an or, right? If you know you either have a dog or you have a dog, well, the only way an or is going to be true is if one of them is true. So you automatically know, well, they're the same thing. So you automatically know you must have a dog. And so reiteration lets you just say, okay, if I ever have P, I can just right away say P and P. I could also say P or P. This rule is actually, it's really rare that we use it. I mean, there's a reason it's just kind of, you rarely ever want to say, oh, because you believed P, you believed P and P. Like that just, it comes up so infrequently. but I think it is necessary for like rare instances. Okay, finally, we can end on material equivalence. And material equivalence is just how, notice none of the rules we've done deal with that biconditional. The biconditional is just one that says, remember, so a biconditional is just A if and only if B. And the way to understand a biconditional is just, well, it's two conditionals. So there's really two different ways we can interpret this. And we didn't talk even much about translation, but about this in the translation video, but I mean, hopefully this will make it clear. A biconditional, you can think about it in two different ways. You can either think about it as either A and B are both true, A and B, or it's not the case that A and it's not the case that B. So right, this is either they're both true or they're both false. So another way of saying this is either A and B, or not the case, A or B, right? Because De Morgan says that these two things are the same. So material implication, equivalence, again, let's just substitute, I believe the form that most textbooks use, including the one for power of logic, is this one and not the other form of not both, or neither nor. But there's another translation. We could also think about it as just two, it's a biconditional. It's two conditionals. It's A if and only if B. So A only if B and A if B. So which means A if B, we need to flip the order, right? So a biconditional, so A if B, A only if B. So this one would be A arrow B, and this one would just be B arrow A, right? Because for if, we always flip the order. And so if I'm trying to say A if and only if, I'm literally just saying these two things. I'm saying this and this. So I'm saying that and that. And you smash them together, and that's how you get this cool biconditional symbol. It's going both ways. The arrow's pointing from B to A, and it's also pointing from A to B. So biconditional is really just two conditionals smashed together. And so material equivalence, we can do it in two different ways. You can either substitute your biconditional with two conditionals like this, or you can substitute it, or I should say, with a conjunction conjoining two conditionals, or you can substitute it with a disjunction conjoining these two conjuncts. Now, typically speaking, I think it's actually going to be more useful to use this lower one. And the reason is because, well, I mean, let's just think about it for a quick second. If you have a premise that's, let's say your premise is A if and only if B, you know that A is true, and you're just trying to conclude that B is true, right? So this is, I should have been doing more of this, just putting in the conclusion at the end. I apologize for it. But the idea is A is true only if and only if B is true. They only come and rise together. So you knowing too, like you already know B has to be true. But the idea is we need to show that using our rules of logic. We need to be very meticulous. We don't have a rule that just does modus ponens on a biconditional, right? Modus ponens only works if this was a conditional. So let's go ahead and get that. Instead of just getting more rules, the idea is we're just going to use the rules we have and be able to say the same thing. So the first thing we're going to do is take one and we're going to break it apart into the two conditionals we know we have. So that's just one ME. And then notice what we just got. When you use this form of ME, you don't get an or with two ands, right? You get an and with two conditionals. So because it's an and, we can right away just simplify. These are just both three sim. And actually, we didn't, if you're thinking ahead, you don't actually even need to do this second simplification. And why not? Because as soon as you got to 4, you should be able to notice, awesome, rule match. I have A. I know that if A is true, then it gives me B, and that's a perfect match for Modus Ponens, and all I wanted to do was just get B at the end of the day. So line 5, I wouldn't even, I mean, as you're learning, sure, do both forms of the sim. Always take both sides of the conjunction down. But as you're getting better, line 5 or line 6, depending on if you had that extra line in there, is going to be just Modus Ponens on 2 and 4. Okay. Okay. So, I know we didn't really get into any specific or too many specific examples of proofs, and I'm not super like, I mean, I would have loved to do that, but like what I wanted to do was make sure you guys had a source of just being able to look at what these rules, how these rules work, that you could be able to rewind and watch again, at least some sort of an explanation, because I know a lot of you are just very much not clear. But hopefully just paying attention to just like, especially the Modus Ponens explanations, just explains just generally how these rules work. I'll just say, I'm just gonna go ahead and do one last example just to really drive home the fact that we're carrying, like, what we're watching in these rules, and that we're watching like the main operators and things like that. And then, but going forward, I'm going to do more examples in the next video where I talk about subproofs and stuff like that. But for now, I'm just going to talk about a little bit more on, right? So I'm just going to throw out a random argument I'll make up on the fly. So if A and B are true, then not the case that R is. Okay, and then let's say that either C is true or R is true. And then and let's have A, and let's have right, let me just try to finish this up real fast. B and D. Okay, so these are going to be our premises. So yeah, so we didn't, again, I'm not going to be able to talk too much about just proof strategy. And I think when I do the subproof videos, that's when we'll talk more about just general proof strategy. But I just want to make sure we're all comfortable with just how these rules work generally and how we apply rules to lines to get new lines. So these are all premises, which means we just start off with them. We don't need to give any justification. We're not trying to prove these lines. It's a weird question or weird thing I hear people say like late in the semester is like, yeah, so then how do we prove premise 2? And it's like, what are you talking about, prove premise 2? We're not trying to prove premise 2. Premise 2 is something we start off believing. We're trying to prove something down here. And in this case, I'll just say our conclusion is C and D. I want to prove to him that C is true and also D is true. This one statement that C and D are both true. That's what I want to prove to him. We're both starting off believing these premises. So that it doesn't make any sense. It's so weird that I hear people saying, how do I prove this premise or something? It just doesn't make any sense. You might ask, what am I supposed to do with this? Why is it even there? But that's just, how is it going to help me? It's not like you owe it anything. It's, what does it owe you? So we're going to think about what can we do with these premises in order to get ourselves to this conclusion. So the first thing to notice is just that we have an obvious simplification ready and waiting. So simplification is going to be a great first thing to do in these proofs. And it's simplifying. It's breaking these things apart so that we can actually use them. Like you might see, oh, I wanted to do a modus ponens right here. You know, I've got A, and A and B give me R, and I got A, I got B, but we can't do a modus ponens yet, right? Because we don't have, in order to do a modus ponens, right, if that's how you approached this proof, if you came into this proof and you said, I want to do a modus ponens, then, well, you would look and you would see, oh, I only have one conditional. So modus ponens, you know, it needs to look at a conditional, cool. And further, it needs, in order for modus ponens to work, it needs to say you have the left-hand side of that conditional on some line. You have exactly that left-hand side on one of these lines. And so if you wanted to do a modus ponens, fine, like let's go ahead and do the check. All right, here's our conditional. Here's the left-hand side. Is the second line the same as my left-hand side? No. No. Third line? No. Fourth line? No. So no lines are exactly the same as my left-hand side. I cannot do a modus ponens right now. I cannot touch this conditional up top because I don't have the full left-hand side. I don't have the negated right-hand side. I don't have anything. So I can't do anything with that. What I can do is simplify 4. So I'm going to go ahead and do that twice because that's just a great thing to do with simplify because it gets all the juices out. So first we do sim 4, and then 6 is going to be D. We're also just getting that from line 4, and then 7. And now let's start to think a little bit. Well, first of all, you've already proven D, and that's half of the conclusion. So let's just put that in our back pocket. Like, okay, at the end of the day, we're going to get to the last line in the proof, right? It's going to just be line number, right? And we're going to want to say C and D. And, well, one good idea, and we'll get more into thinking like this in the future, but one way to get to C and D is if I did some sort of conj. And I already know one line that conj is going to cite. It's going to cite line 6, right? Because all I'm going to do for a conj is I'm going to just point out where you have either side, and I'm just going to smash them together. So now the only question is, where am I going to find C? I just need to get myself to C, and then I'm just going to conjoin these two things together, and then I'm done. Right, so that comment. So this is going to end up being just 6 question mark, and it's just about where am I going to be able to find C? Because as soon as I find C, I'll conjoin them together, and I'm done. Okay. So now we need to find C, and now maybe it's a little clearer. So now we still can't do a modus ponens, but this is where the problem solving comes in. The idea is now you have A and you have B. And if you're good about your rules, if you're familiar with your rules, you know just by that you can put them together to say A and B. And why would you want to put them together to say A and B? Because you remember when we started off the proof when we were like, oh, it'd be nice to do a modus ponens. So it'd be nice if I had this left-hand side of the conditional. Well, now that I have A and I have B, I know I'm familiar enough with the rules that I can get myself A and B just with a simple conj. And then right away after that, I'm going to do my modus ponens. Right? So on 7, we're just going to right away do our conj because we're preparing ourselves to do our modus ponens. So this is just going to be 3 and 5. And then we're going to take this and we're going to say, okay, well, again, we have a conditional. We match the left-hand side of the conditional with something we already have. And that gives us the right-hand side of the conditional. Right? So I needed to build this so that later when I go to the big conditional store and it tells me, oh, you want to buy not R? You can buy not R. You just have to pay for it with A and B. So I got my money together. I got A and B together so that later on I could, so now that I have them together right here, I can go to 1 and I can say, hey, 1, look at 7. Now modus ponens better give me the product. Okay, let me throw away. So understanding how modus ponens works, I mean, really, if you don't understand how modus ponens work, it's really not even about modus ponens. That means you're just kind of not understanding how the rules work in general. And I mean, you know, everybody takes their own time in getting used to these. So like I'm stern about like you need to be comfortable with this and that, and you need to be able to see this and that. And if you don't, you're just not getting it. And everybody takes their own time to be able to get these things. But just these are what I mean when I say those things is that's where you want to be able to get to. And if you're not there, that's fine. What's not fine is if you're not putting the work in order to get yourself there. So right, this is just going to be a 3-4 conj right there, and then we did. And so then again, I'm gonna just, I know this is overkill, but I'm just gonna do this in color. We have if the left side, then the right side. I don't care how complicated the left and right side are. All that matters is the conditional is my main operator. That's all that you should be checking when it comes to these inference rules. And then you come down here and you see, oh shoot, I actually do have that left side. So modus ponens, right? Modus ponens just says, if you have this, if this leads to that, right? That's modus ponens right there. Forget all the stuff, junk, everything. All modus ponens is if you got left and there's an arrow in between left and right, right? If this is just a conditional sentence, and then you actually have whatever the left side of that conditional is, then you get to give yourself the right-hand side of that conditional. So it doesn't matter how complicated they are, we just need to make sure we're treating them as a unit. And so down here, we need to give ourselves, yeah, let me go ahead and put it like this. We need to give ourselves not R, right? We need to give ourselves whatever it is that's on the right-hand side of that conditional. So again, you really need to pay attention to what the main operators are. That's what allows you to tear things apart. So often I see people like trying to utilize the A that's in line 1, and it's like, what are you, that's so far nested into the sentence. You need to first pay attention to what are the main operators. That's how these rules work. They work by just fitting patterns like this, where these operators are the main operators of the various sentences. Okay, so now that we have not R, we have a near miss for DS. So remember DS, so I'll go ahead and put that one over here. So DS says, okay, if you have this, bam, bam. So, right, well, I'll put that stuff was just a note for us to do later, but I'll put it back. So DS works like this. Again, let's just go ahead and forget about all the extra stuff. It says if you have an or statement between two things, and then you've negated one of those things, well, you get to give yourself the other thing. So we can go over here and we can look. We have this or statement. Here's the right side. Here's the left side. And down here, so now I'll erase these highlights. Oops. Right? And so down here, we have a near miss. Or excuse me, actually, no, that's a perfect miss. That's not even a near miss. Right? Because all we have is, right, so let's go ahead and put this in blue. We have not R down here. Well, what's the green box? When we look at what we're supposed to correspond to, we have, that's our green box. And so in fact, we have a perfect match for DS. Look over here, right? We have this or statement, and then we have one of the sides being negated, right? We have this or statement, and then we have one of the sides being negated. And that's what gives us, at the end of the day, the pink one. Because you checked the box for both the first two lines, you're now allowed to give yourself the last line. And the last line, it's not, there's no extra tilde or anything like that. We're just going to give ourselves exactly what we are supposed to have, exactly what's in the pink, and that's just going to be C. Right, okay. So now, so you should be having this sort of lens every time you think about a rule. You should be like looking over and just saying, okay, which side is my left side, which side is my right side? I don't care how complicated the sentence is in between. I can't get in there until I've actually done these implication rules. Or if you want to just look in there and do an equivalence rule. But yeah, we can talk about techniques and stuff as we go. So now we have C. So now let's go ahead and finish. So we have 9 is C. So that means 10 is when I'm going to just do C, and D is going to be 6, 9, conj, done. Right, so all that we did in that proof was we first noticed, hey, I've got an easy simp. Let me start off by doing that. Hey, I got a near miss for Modus Ponens. And so let me just build what I need to get there. And then I've got a perfect match for DS. So let me just do that. And then we just conjoin. And again, I mean, the real reason why I went through this example is just to give you more experience thinking of these rules in this format, that it's just if left, then right, you have left, that gives you right. And that's all Modus Ponens is. And so like you should be having like colored lenses when you're scanning the proof. You should be thinking about it in terms of, yeah, actually this is nice that I can, oops. So you should be thinking about it as if you're just taking this structure and you're just like scanning over the entire proof. Do I have a match there? Do I have a match there? Do I have a, here's my only conditional, so that's, what that has to be on. And then you're moving the red guy and stuff independently. But that's the idea. And the same thing down here. You're just going to take this and you're going to see, okay, I've got an or right there where my R is the green part. So cool, I've got negative R right there. And so that means here I'm supposed to be able to get out the red part from that, and boom, I get out the red part from that. So you should have this mentality of like holding over these, like, here we're not able to like put spaces in between the lines, but like still the mentality of like scanning just for matching the pattern of the rule is what you should be doing. Okay, I'm gonna go ahead and stop there. Next time we'll talk about subproofs as well as proof techniques, and we'll look at a lot more examples, but hopefully this at least gets you started on what the point is of a proof, how the rules are supposed to work in sequence, and just generally what you're not allowed to do. There should be a lot of things that you should know are just completely ill-formed. If you're ever not exactly sure what rule you're using, then you shouldn't be doing what you're doing. That's serious. And if you're ever not exactly sure how many lines you're citing for that rule, you don't have a good enough grasp of that rule yet. You really should slow down and verify, why am I using this rule and why do those lines give me my new line? Why? Because each of these rules should be really innocent in themselves. So that should be a story you're able to tell every time, right? Each one of these, the whole point of doing this proof is that each one of these steps is something that it doesn't matter how simple this guy that we're talking to is, how stupid that this guy, each one of these steps should be really innocent. So he's like, yeah, I get it, because of line 4 and this simple argument that you're making, yeah, I'll believe B. Yeah, because of line 4 and that simple thing, I'll believe that. Because of those two lines and that simple rule, I'll believe. So every time you have a new rule, you should be patient and just convince yourself why each of those rules works. And that's going to be very vital in actually getting comfortable in these things. Okay, again, go ahead and send me any and all questions that you have on this.